qu'il a donné à Quiberon là, au mois de septembre, magnifique, sur le contrôle des écoulements cisaillés. C'est Navier-Stokes, on est juste au-dessus du Reynolds critique, ça commence à osciller, et donc il identifie le mode instable et fabrique, tu me corriges si je dis ça, une équation d'amplitude qui résume la dynamique sur le mode instable, et il cherche à introduire une perturbation adéquate dans l'écoulement pour arrêter les oscillations.
C'est exactement ça.
Et il fait ça pour Navier-Stokes, et à visée pédagogique, il le développe complètement sur Ginzburg-Landau. Et moi, j'étais enchanté de ce cours. En plus, Denis expose vraiment très bien. Si vous avez l'occasion d'assister à ce cours, je vous le recommande vivement. Voilà. Donc Denis Sipp est un ingénieur de l'armement qui a fait sa thèse avec Laurent Jacquin-Patricuère. Il a fait sa carrière sur Navier-Stokes. On peut dire ça.
On peut dire ça, j'ai...
Et donc essentiellement à l'ONERA. Donc son activité principale a été le contrôle des écoulements cisaillés, mais aujourd'hui il parle d'un sujet plus récent qui est lié à des problèmes inverses, et toujours sur Navier-Stokes. En fait, en l'écoutant à Quiberon, je me disais, mais finalement, dans le séminaire, sur la partie fluide, il y a assez rarement de séminaires qui traitent de Navier-Stokes. Je me suis dit, ça serait bien qu'il y en ait, et je me suis dit que Denis était le parfait candidat pour ça. Je te laisse la parole.
Merci Patrick. Alors je vais parler en français à moins que... I prefer... Okay, I will speak in English, okay. This is actually, so we talk on flow reconstruction using data assimilation and resolvent analysis. And actually this is not my historical subject, as Patrick told you. I came into this because I am actually a specialist of optimization of adjoint methods. And in the years 2010, okay, I can go this way, okay. Okay, so in the years 2010, I was looking for more applications of that kind of techniques. And in my department at ONERA, it's a particular place because there is both experiments with wind tunnels and also CFD. And at that time, I knew that CFD modeling was not that good sometimes because you have models which can be not very accurate. And in experiments, you also have problems because you also have uncertainties. Okay, and so at that time, I was saying, well, I know how to do optimization. Why not try to use optimization to make a good interplay between CFD and experiments? This is what I will present you here. So this is also a common work because I'm not the only. In what I would show you, there are some experiments. Benjamin Leclerc is an experimental guy. There is a PhD student, Lucas Franceschini, who has just defended. And these are two, Samir Benedin and Olivier Marquet, are two people little like me, theoretical guys, more enumeration. And this is a little common work. So here I have two experiments. I will show you a little what is ONERA, okay, which is not exactly. So I have two slides. One which is more what is experiments. So experiments in facilities like large wind tunnel facilities, and also what is CFD at ONERA. So experiments, typically we have that kind of wind tunnels at Meudon, where we have models, and this is a large wind tunnel, which is something like 2 meters or something like, maybe not 2 meters, but it's something which is large. And in that kind of facilities, you have, my point is to say that you have lots of uncertainties, actually. This is the focus of what I would say, and I try to show you what kind of uncertainties you have. So if you have models, of course, you also have measurements. You have lots of different techniques of measurements. Typically, you have pressure sensors. You can also have paintings so that you can look at the pressure of on the whole airfoil. You can also look at the temperature, also on the surface with temperature sensitive panes. And you have also lots of small sensors, Q-light sensors for pressure. You also have accelerometers, static pressures, and so on that kind of thing. And also you have field measurements. Typically, for example, you have cameras with laser sheets. You can have velocity, density gradients inside that kind of wind tunnel. And typically, all these measurements have uncertainties. Of course, there are error bars, okay? But even on the model, you have uncertainties which come from usually boundary conditions. You don't exactly know what are the upstream conditions. You can have turbulent features. You can have unsteadiness, non-homogeneities. Even the model will vibrate and deform so that you don't exactly know exactly what is the exact state of your flow. But on the other hand, it's truth, because you have the exact Navier-Stokes equations which are solved by the fluid, okay? So you cannot say that there are modeling errors, but you have other kinds of uncertainties, okay, in experiments. If you now go to more the computational side, of course, if you are on a very fundamental area, you will try to resolve every scales of your flow. And then, of course, there are not many uncertainties, but still you have some of them. You can have discretization issues. The scheme, you can, when you solve your Navier-Stokes equations from one time step to the other, you can do it nicely or approximately. But even if you go, but this is very, very expensive. So usually what people try to do in industry is they try to model scales of the flow. And then you go, the more and more, you go from DNS, then you go more and more to the bottom of this pyramid. And at the end, you have what is called RANS models. And RANS models, you have turbulence models like K epsilon, K omega, you have lots of them. And here, of course, there is much more uncertainty, okay? Because these models have been tuned on very simple flows. And if you try to apply them on complex configurations, they can be completely out of, they can be they can give very strange things. So there is a balance between the cost and accuracy, okay? And uncertainties, of course, you have more and more uncertainties the more when you go towards RANS, U-RANS, okay? And finally, you still have uncertainties which are also linked to the boundary conditions. For example, you don't exactly know what is the upstream flow and things like this if you want to compare to the experiment. So you have, again, uncertainties there which are a little reminiscent of the boundary conditions that you had here. So my whole point here is to say that you have uncertainties in the both of these worlds, experiments and CFD. And know if you, what is data assimilation? Data assimilation is try to make a close interplay between the CFD world and the experimental world. So you have a wind tunnel, you have measurements, and then you have also a computer where you solve a model, and you know that your model is not good, okay, not sufficiently good, and then you try to put these two results together. Okay, so data assimilation will be, for me, it is tuning the uncertain parameters in the CFD. So we have uncertain parameters in the CFD model. So we tune them, we optimize them in order to match given measurements that come from the experimental world, and of course within the measurement uncertainties. So we take into account both uncertainties, both the ones which are in the models, and also the ones which come from experiments. And to do this, there are usually two ways of doing that. There is more the optimization world where I come from, and I will only deal with this. But there is also another world which is ensemble-based methods. This is ensemble Kalman. There are lots of techniques there, and all these techniques come from meteorology, actually. And but basically, these two approaches, they do the same thing. they make optimization, but in a different way. So for example, if you take the ensemble methods, the uncertain parameters that I told you, so if you have uncertain parameters, they are represented, for example, as ensembles of members. So for example, this is x1 and x2. These are two, let's say, locations which are unstable, two parameters which are uncertain. Then we model this uncertainty by putting 100 members within this small round box. And then we have a model, and then we propagate these uncertain features into another space, which is there, which is here. And then at some point, we take into account the measurement uncertainties, which is the red thing. And then basically what the ensemble methods, ensemble techniques do, the update is the intersection between the two. So you can see that basically we make a compromise between the uncertainties which are in the model, which is the blue, propagated, and the uncertainties which are in the measurement. And then finally, it is taking the intersection or something like this. Okay, so this is done by it's done like this with ensemble methods. But if you take variational methods, they do exactly the same. You have still x1, x2, but finally at the end you make an optimization which combines the two uncertainties. You see, you have the measurement uncertainty, which is here with a measurement covariance matrix, which is basically the size of this round stuff. And then you have also state covariance, the state covariance part, which is here with the state covariance matrix, which is here. And then you make a compromise between these two uncertainties. And then at the end, you find the same minimum. Okay, so I will be doing only this part because, as I told you, I know well optimization, variational methods, and optimization. But you can do also the work with the ensemble methods. What is nice with the ensemble methods is that you can take just CFD tools as they are, propagate, and it's not at all intrusive, while if you do variational methods, you need adjoints, you need to have advanced tools. And this is usually easier if you have a code where you don't want to go inside. Okay, so it's easier to do that, but this is a little more tricky. But at the end, well, there are pros and cons in both methods. So I will only develop what is there. So applications, I just wanted to tell you that data simulations comes from the meteorology, the world of meteorology. And then since 2010, there have been first applications of data simulation to improve measurement techniques. For example, measurement techniques today, of course, they become more and more sophisticated with camera everywhere. But what people do today is that they combine these measurements with CFD models, and they do exactly the same. They do data simulation, and then they improve their measurements by a model which is around. Okay, and this has been started. These are people at Rennes, at INRIA Rennes, who do that. It's Etienne Mémin, Dominique Heitz, so they are specialists also of this. And in aerodynamics, so the world where I live at Onera, things started in 2013. So Kato et al. is one of the first guys who did it with ensemble methods. So he is already in this kind of world, and then there are other things like this. So now I would like to show you. So this is a particular world of Onera, which is really the industrial part, the wind tunnels at Onera, which are modern. You know that Onera has very big wind tunnels, which are dedicated just for industrial people, for development of aircrafts. And usually, these are not research wind tunnels. That means that you have very complicated models, but you have very few measurements, okay? And usually, when you go to modern, the only measurements you have is load balances. So force balances is just CZ, CX, and lift and drag. And then usually you have some CPs. pressure coefficients. And on top of that, you just have the mean value. Okay, you just have the mean value. They don't care about the variance, standard deviation. They don't care. They just want to have the mean CZ, the mean drag, the mean lift, and the mean pressure, because it's exactly what they need for the development of their aircrafts. So the basic time average. It's time average in time average. So these are only time average quantities. And finally, to make data simulation, there is one choice. We could, in terms of model, what do we use? Do we use a DNS model, which where there is lots of fluctuations, or do we use a RANS model? But here, as they are only interested in a RANS model, in finally time average quantities, so finally, why not try to take the RANS approach with turbulence models? And the advantage of this is that it's quick. And what basically they want is that in 10 years, they would like to provide their wind tunnel, but a wind tunnel with data assimilated quantities, so that when they have a client, they come with this, and finally they go back, but with the full flow field, time average flow field everywhere. Okay, so there is a kind of competition between the big wind tunnel providers, Onera, and there are lots of others, and this is a way of having a better product. This is what they, so at Onera, this is data simulation has become since 2014-15 a very major thing, just because of the future of the big wind tunnels, which are at Onera, because if you don't make progress, finally at the end there are other people who will do it, and they will not have any more contracts and things like this. So there is, I just wanted to tell you that there is a real issue about people and the future of wind tunnel testing. Okay, so this was to say that I will go to the RANS approach, and of course in the RANS approach for turbulence modeling, there are lots of uncertainties. This is what I would like a little to show you here. I just want to introduce you what is Reynolds average Navier-Stokes equations. What is this RANS approach, just to show you. So it is based on a Reynolds decomposition. So if the full flow field, you divide it into a time averaged part and fluctuation. And then if you throw that inside the Navier-Stokes equations and you take the mean, of course, you have the equation that governs the mean, okay? But at the right-hand side, you have turbulence stresses, okay? And usually, people model them with a turbulence model. So the problem of data simulation is predicting well these turbulence stresses, okay? So I will optimize things that are related to these turbulence stresses, okay? So that the outcome of this model, which is U bar, complies with my measurements. Okay, so it's exactly how I will see this optimization problem. And this is just to give you some results. For example, if you have 0 Reynolds stresses here, so this is approximately a Reynolds 200, just to give you a hint. This is at Reynolds 200. If the stresses are 0, you have a huge bubble because it's a laminar bubble. Of course, if you make the full DNS, you have fluctuations. That means that the Reynolds stresses are non-zero. Okay, and if you have a good approximation of these Reynolds stresses, you have the good mean. Okay, and of course, you see if you have the good stresses or the bad stresses, the mean value is completely different. Okay, so if you make an error on the prediction of these stresses, immediately you have an impact on the time averaged flow that you compute. Okay, so this is data simulation within a RANS framework. So to me, it's exactly what I told you. It's tune the Reynolds stresses such that the mean flow, the U bar, is as close as possible to external data. So this is my optimization problem. Here, I start with 0, and then at the end, if I have a good evaluation of these Reynolds stresses, I have the good mean. Okay? So, to tune these Reynolds stresses, so either I do it from scratch. This is what I will do in the second part with resolvent-based methods. But I will start in a more classical way, which is there. That means that I have a turbulence model, which is the green part here. So I have a K-epsilon model or spiral mass model. I have one. But I know that he's crap. Okay? So I will add tuning parameters, which can be either here, or they can be at different levels. I have to make a choice. So I will introduce tuning parameters, and that will correct a turbulence model. So why do this? This comes from the fact that usually turbulence models gives you a good order 1 representation of the flow field. They are not completely crap, okay, turbulence models. They give you approximately something which is good, but not exactly good. So finally, starting from an existing turbulence model and tuning, correcting it slightly, might work in most of the cases. Okay? While this work, it's much more difficult because you have to create, by optimization, the whole Reynolds stress. And so this is much more difficult to try to tune the full Reynolds stress tensor. While if you have a turbulence model, let's say 80% of the job is done, and the last 20% you do it by optimization. While here you have 100% of the job to be done by the optimization. Okay, so it's easier to start with something that exists, and we know that turbulence models are not that bad. They are bad, but not completely bad. Okay, so these are my two parts. First, data assimilation with turbulence models. This is the part that I showed you here, and then data assimilation based on resolvent modes, and this is a little more difficult and a little more fundamental. So now I start with this, and here I show you again the Rance equations, okay, with this Reynolds stresses. Now I go a little more into the modeling, turbulence modeling. I don't know if there are lots of people still doing turbulence modeling here. This was really a big area in the last century, at the end of the last century. Now there are fewer people now. But here, usually what people do in turbulence modeling, they first do a Boussinesq approximation. It's not mandatory, but you can do it. And most of the turbulence model are done by doing this approximation. That means that the Reynolds stress tensor, which is here, we make a Boussinesq approximation and say that it is the Reynolds stress tensor is parallel to the symmetric part of grad U bar. And then what is introduced, it's what is called an eddy viscosity, which is like the laminar viscosity, but it's a viscosity, an increased viscosity, which is due to the fluctuations. Okay, and then at the end, you just need a model that gives you the evaluation of this eddy viscosity. And here, what we take is basically a spiral Maras model. That means that we have nu t here, and this is a model that gives you the evaluation of nu t in the whole flow. And then you need to solve all of this. Okay, so just to make a comment, people who make turbulence modeling today, they say what is really crap is the Boussinesq approximation because turbulence stresses are nearly never Boussinesq. Okay, so you can do this with, of course, with other models. You can also do that with more sophisticated models, Reynolds stress models and things like this. But here we started simple with the Boussinesq approximation and just a one equation model, which is the spiral Maras model. Okay. And here we'll just show you some deficiencies of turbulence models, even in simple cases. So because usually people say turbulence models are good as soon as the flow is attached. Okay, this is usually what people say. Here I have two slides to show you that even in this case, the models that we have are not good. Okay, so even in this case. So for example, I start with on the left. This is the Reynolds theta. This is the Reynolds number based on the momentum thickness of a flat plate boundary layer. So the more you go on the right, the more the higher the Reynolds number. And this is the friction coefficient on the plate. That means that it is the derivative at close to the wall. It's the friction close to the wall. And there are experiments, lots of experiments there, and you see that the experiments follow a trend, and the mean trend is given by the black line, I think, something like this. And if you take a Reynolds model, a turbulence model, which is the Spallar-Almaraz model, which is one of the most common guys, which is taken in industry, you can see that if you go to high Reynolds number, very high Reynolds numbers, you have errors that can go up to 5 to 8% in terms of friction error. And you know that Airbus and when you design new models, you want to have a very, very accurate prediction of the drag. And of course, if you cannot afford for 8% of error on friction, okay? And so this is already a huge error. On the right, this is another error that is quite common, is that all the turbulence models have initially been tuned on zero pressure flat plate, on zero pressure gradient flat plate boundary layers, okay, or on mixing layers, which are very simple. As soon as you have accelerated boundary layers or decelerated boundary layers, you have immediately errors, okay, and this is what you can see here. You have the truth, which is the red line. That means that you have here a bump. The flow comes from the left. And the question is there separation in the back of this bump? Does the flow separate? In truth, if you look at a true solution, there is no separation because the friction coefficient does not go to zero in the red line. While if you take standard turbulence models like K omega and things like this, you have the red curve, you don't recover it at all. Okay, and there are some of the models, the most easy, the K omega SST, which is also a common one. He predicts separation, so that there is a separated bubble on the right, and while in truth there is not. And this can have a huge impact on the solutions because friction is also linked to separation, because if you make a mistake in the friction coefficient of close to the boundary layer, if you make an error, of course it would separate more or less early or late, and then you will have lots of impacts on the loads and on the drag of the full solution. So this is just to show you that even in simple cases it doesn't work. Yeah. Yeah. No, go. Yeah. No. Oh, sorry. Separation is just if you have a bump like here, there is a flow field that comes from here. Okay. Here you have a boundary layer, and the question is the flow field remaining attached? That means that at all locations you have dyu is superior to 0. Okay. Or if it separates, that means that you have a recirculation bubble, and then at some point you can have a dyu is lower than 0, close to the wall. Okay, so separation is this. Okay, and this has a huge impact on drag, lift because between an attached flow and the separated flow, usually you have two different worlds. Okay, you have something that works when it's attached, and as soon as it separates, usually all the performances of airplanes, turbomachinery, and things like this, they go down. And usually it's prediction of separation, which is it's what people want to well predict. It's predicting separation. And predicting separation goes by a good prediction of the friction coefficient, which is nu dyu. This is the 2. This is the friction at the wall at y is equal to 0. So we need to well predict the friction coefficient, and then you well predict where it separates. Okay, and this is just an example. This is the friction coefficient. Red is the true one, and blue are models, and the others are models. And as soon as you go below 0, that means that it separates, and this is bad because in red it's okay. Okay, so there are errors in modeling. You have errors even in very simple cases. That's the point I wanted to make here. I don't even speak of more difficult cases where it can be completely stupid. So as there are errors, that was my initial model. Now I will add tuning parameters to allow me recover the truth. Okay, and these are the two guys here, either this one or either this one. So if there are specialists of turbulence modeling, correcting the turbulence model at this stage, at this level, or at this is not at all the same. Okay, because if I do it here, I am still within the Boussinesq approximation. You see, if I correct here, my stresses follow still the Boussinesq correction. And while if I correct here, I can correct the Boussinesq deficiencies. Okay, depending on if I do it here or here, I will have different results. Okay, and I will try to show you these different behaviors, either if I choose this or this. Okay, so this is my optimization slide. Okay, it's my objective functional. This is you see I have forces that I optimize here. Okay, so I have J of F. This is my cost functional that I will try to minimize. And here I will minimize, so M is the true measurements I have. Okay, these are the measurements, ground truth. And this is the measurement that come from my corrected model. Okay, so my model is here. It's the Rand's equations with a turbulence model with two tuning parameters. You see I have F nu and F nu t. I have two tuning parameters. And what I will do is that I will tune Fu and F nu t such that I will minimize this, okay? So just to show you also, I didn't consider here state covariance because we started, but you can also add here, you can do the full game, which is minimizing the balance between the uncertain measurements, the uncertainty within measurements and the uncertainty within the state. Here we did it a little more simply. And to make this minimization, basically we do adjoint methods because you see this Fu and F nu t. These are there are lots of degrees of freedom here because these are functions of the space. So we have lots of parameters, we have lots of degrees of freedom to optimize, and to make this in an efficient way, we compute grad Gu Fu, grad G F nu t by adjoint method. So here comes steps in the adjoint techniques. And then we need also a technique to, once we have the steepest descent direction, we need to go into this direction, and this is done here by low BFGS method. I will not go into this, but everybody uses this. Okay, so you need a gradient and you need LBFGS, you put this together, and then the algorithm tries to find, to go down. And this is basically what I will show you on an example, okay? So my example that I will take here is, so it's a backward-facing step, so it's quite simple, okay? The flow comes from here. It is at Reynolds 28,000, so it's turbulent, okay? We have fluctuations, so there are Reynolds stresses. And this is a DNS that has been done, so it's ground truth, okay? So, and if we take the time average, the mean of this fluctuating field, it's what we have here. So, okay, this is the ground truth. There is a small bubble, okay, and if I and here I have extracted DNS and DNS. I have looked at quantities of interest, usually to fluid dynamicists, which are the friction again along the wall, which is a very important thing, and also the wall pressure along the wall. So here, this is the black line. And of course, what we want is to make the model match with these measurements. And if you look at the scalar mass model, the model that we had here, which is a very common one, without tuning the parameters Fu and F nu t, you have a bubble which is completely different. Okay, you see you have a big discrepancy between the prediction of a model and the ground truth, which is quite different. Okay, you see there is a big difference, and you have also this big difference at the wall friction and also wall pressure. Okay, so now we tune, and we tune in the case of two different kinds of measurements. First, we take a toy problem where we know the whole flow field. Okay, so we have lots of measurements. This is, for example, the case of a PIV setup. A PIV setup is you have a laser sheet, and then you look at the measurements a little everywhere in the flow field. And then you have this is this case, and then afterwards we'll take a second case where we just have measurements at some points. Okay, and here comes the inverse problem. Okay, we will see that immediately. So we start with this. So these are my two ways of correcting the model: either the blue one, which is the Bossinesc, either the turbulence model correction. You see, it's I take this, either I tune here or I tune here. Okay, and then this is the cost functional, how it goes down, and immediately you see that if I correct here at this level, I can go down much more as if I tune here at the level of the eddy viscosity. This is really easy to understand, is that if you tune F nu T, it will just change the eddy viscosity, but you are still constrained in the Bossinesc approximation. And you are very constrained. Your model is very, could say, rigid. That means that you can do a little whatever you want here. You are not able to change a lot U bar because you are constrained to changing just the eddy viscosity. While if you allow changing things at the FU level here, you have much more freedom and flexibility to affect the U bar solution. And this shows you why here, if you make, these are some iterations of the optimization algorithm. Here you arrive at something which is quite small, and here it's a little more big. So these are just the results. That's the initial Ron's Spalar-Almaraz. Now I tune, and then you see before that was at the beginning, big change. Up, it's a little better. But this is for the turbulence model correction. Okay. Now if I go to the Bossinesc, which is the blue one, initial turbulence correction, and this one is very perfect. Okay, so here you manage to exactly recover the size of the bubble. You nearly recover the wall pressure, and you nearly recover the wall friction. Okay, so that's in the case where I head everywhere. Of course, this is not our objective, because in wind tunnels usually you have very few measurements. Okay. And so in this case, now we treat this case where we have few measurements, and you have, but you still tune these two functions. And in this case, well, we'll see that the models react a little differently, but it's still very easily understandable. If you take the Bossinesc correction, which was the best guy here, you see, we managed to do everything, because we had a very good authority on changing things, okay? But it is so flexible that when you have few measurements like this, there is a kind of thing which is called a little overlearning. And if you have just few measurements, the Bossinesc correction, which is so flexible, there are many inputs, finally few outputs, the model is very flexible, and then it doesn't work, okay? If you take the more rigid model, okay, the guy with nu T, where you don't have a lot of action, actually, you don't have a lot of authority, you have still many inputs, still few outputs, but this time the model is much more rigid, and then it works better. So depending on how many measurements you have and how many inputs and outputs and the model you put in between, you have to be clever to make that everything is aligned. So for example, here you have many inputs, few outputs, and rigid model, it was okay. While here you had the flexible model, and then it doesn't work. Okay, so then you can still cure things. For example, if the Bossinesc approximation was very good at the beginning, you can still make it better by adding terms, penalizing the gradients, and then it works again. And this is what finally we did with respect to what we had in blue before. we had a flexible model. It's still flexible. We had few outputs, but this time by penalizing the gradients, we finally had fewer inputs because we didn't let the optimizing force go into whatever direction. We said that we just want smooth F, okay? And this is also a way of putting information on the state. This is the state covariance matrix, and we give information. What this just means is that the Navier-Stokes equations that we have, there is not enough information there, and we need to add information about the true solution. This is all this what we do is true, but here it's a way of giving information, more information. Okay, so that was basically the first part. I don't know how long do I have still. It's okay, a quarter. I will. So this is, it will be a little more physical maybe, no. Here I take I still have my objective, okay? This is a flow field which comes from an LES, and here we have lots of fluctuations, okay? And the first thing I would like to know is what are the coherent structures in this flow field? What are coherent structures? So the basic idea, basically, is to make a Fourier transform, okay, of this flow field. So you have, let's imagine that you have data on the whole vectors, okay, and then you just make a Fourier transform of this, and then you have Fourier modes, U hat of W. Of course, this is not completely well posed because we are not in a space which is L2 integrable with U of T because we have data which is there all the time. So we need to do it in a little more clever way. And the good quantity to introduce actually is what is called the 2.2 time correlation matrix. So we have the data and then we form this matrix, which is U of T plus tau, U of T star, and we take the mean of this. It's like a little the PSD. When you make Welch method, I don't know if you know this, usually you have an F, which is a signal, and then you want to have the Fourier transform of it. If you just make Fourier transform, it usually doesn't work. And then people usually take bins, and then they take the mean. This is just the same thing, but a little more general. So here you have the spectral cross density tensor, which is the Fourier transform of this. And then in the end, you make the SVD of this, and then you have again your U hat, which is the Fourier transform, but a little clean. I'll just give you examples. So this is the LES. And if I make a Fourier transform at 0.7, you see I have this mode, okay? Of course, normally it's complex, so that normally the time evolves. Here, if you do it at frequency 2.1, so what you should see is that this flow field is the sum of different Fourier modes. Okay, very simple. So these are, let's say, these are just Fourier modes. My point now is that these Fourier modes can be predicted by linear stability analysis. Okay, what is there can be predicted by Fourier analysis. And for this, what I will look at is the mean, the time average. So this is the fluctuation. Hop, if I take the time average, it looks like this. Okay, and my question now is, can I predict the snapshots that I showed you, the Fourier mode that I showed you before, with the knowledge, by the knowledge of this? Okay, if I do this, so this is really simple again. This is U is U bar plus U prime, Reynolds decomposition. This is the equation that I showed you before. But if I go to the next equation, which is on U prime, which is the fluctuation, okay, this looks, if you look at carefully this equation, you have on the left, you have the linearized Navier-Stokes operator around the mean. You see, you have U bar here, around the mean. And on the right, this is the rest. Of course, normally this is an exact equation. Normally these two equations are coupled, usually. Okay, but here I throw them away. I do as if they were not coupled. I just know that this equation is exact, this equation is exact. Okay, this is U bar, the mean. U prime is the fluctuation. F prime is the forcing term. And now I look at the Fourier mode. I go in Fourier space, and then I can have a link between the forcing, which is the F hat, and the response. And the operator, which is in between, is called what is called the resolvent operator. It is the linearized operator around the mean, Navier-Stokes operator around the mean, in spectral space. That means that I add I omega. Okay? And this operator is very interesting. Why? Because now if I do a singular value decomposition of this operator, a singular value decomposition is something like this. It decomposes a matrix or a linear operator into three things: an optimal response, optimal forcing, and optimal gains. And these are two orthonormal bases. U tilde is an orthonormal basis, F tilde is an orthonormal basis, and sigma are the optimal gains. Okay? So just imagine we managed to do that in the flow field that we had before. And in the flow field that we had before, if you compute these guys, you can do it, you will see that there is one guy which is very large. The dominant one is very big with respect to the second one. Okay? So that means that this operator is rank 1. So if you do an SVD of this, you just have nearly one dominant eigenvalue. That means that this operator is rank 1. Okay? In lots of cases. That means that, will not show this. That means that the singular value decomposition of RU bar, which was usually this, we can just approximate it by the first term. Because in shear-dominated flows, mean flows, usually this is true. Okay? We always have the fact that there is one dominant singular value with respect to the second one. Okay? And then, once you have a rank 1 approximation of your resolvent, you have 1, because you know that U hat is linked to RU bar F hat. And as this guy is rank 1, you can say that U hat is proportional to U1 tilde. That means that the Fourier mode is always proportional to a quantity that comes from linear stability analysis, which is the optimal response. You see, this is the Fourier mode from the DNS. And here on the other side, this is the guy that comes from stability analysis, which is the U1 tilde. And the fact that this is parallel, because this is a scalar, comes just from the fact that the resolvent operator is rank 1. Okay? And this is something which is extremely common, actually. And this explains why U hat, the Fourier mode, is parallel to this. So this I will skip. This is just a comparison. This is the Fourier mode that I showed you before. And this is the optimal mode. You see, this comes from stability analysis, and this comes from DNS. And you can see that you can predict from stability analysis around the mean the spatiotemporal behavior of the DNS. Okay, so this is something very strong result that we will. So you can do that at several frequencies. This is 0.1. This is 2.1. You see, you have exactly the same. And now we will use this. I will skip this. We will use this for making again data simulation. Okay, because now I will just show you what we will do. Oops, I come here. You see, this was my initial statement. I said that I want to predict my Reynolds stress tensor. Okay? But this Reynolds stress tensor, with the resolvent modes, I can do it. I can say my U prime, by Fourier decomposition, it is a sum of at different frequencies, normally the Fourier mode. Okay? But I just showed you that this was equal to U1 tilde, which is the stability guy. Okay? And so finally, I can have a representation, an approximation, a direct approximation of my Reynolds stress tensor, which is here. These are guides that we can compute, okay? And finally, there is just one tuning parameter, which is the amplitude of each guide, okay? So at the end, I will just have n, if I have n Fourier modes, I will just have n amplitudes to tune in order to recover my measurements, okay? So this is something that I can compute. These are tuning parameters, which are very low dimensional. I don't need any more adjoints here because I have just a few of them. And then we can try to tune them so that at the end I recovered my measurements, so that I can do, again, data simulation, okay? So at the end, I have this thing to solve. This is my mean flow equation with the Reynolds stresses, which are here. These are my control parameters. And this is the definition of my resolvent modes, okay? These guys which are parallel to the Fourier modes. And of course, this is a coupled equation, which is not that easy because this U1 tilde depends on U bar, and U bar, of course, depends also on U1 tilde. So this is a coupled equation to be solved. So this is something that we know how to do. And then at the end, we just need one or two measurements or few measurements to tune the strength of these parameters so that we fix this. And this is done on a very simple example. So here, this is Reynolds number 100. Here, this is a very simple case where we just have few harmonics. So this is a flow field, vortex shading. And this is a flow field that has peaks in its spectrum, okay, which are here. So we approximate our fluctuations just by one frequency, which is the fundamental, okay? And then we try to tune this modulus of A square guy. So, and here we can take very different measurements. So either we can say, I know the length of the bubble. For example, I know that the true length is 2.43. Or for example, I know that the mean CD is 1.47. Or I can have another information, for example, the Fourier, for example, at some point, I can also have the spatio-temporal fluctuation, and I can look at the strength of the fluctuation at some frequency. Okay, so I can take I can take one quantity that I have in my experiment, and then I tune modulus of A, which is my control parameter, very simply, and I look when it matches. And you can see that whatever the measurements you take, it always gives approximately the same value of modulus of A, which is approximately 2.22, 2.25. So you see that here we don't need adjoints because there is just one parameter to tune. And we can even take very crude measurements, which is not even a pressure CP profile. We can have the length of the bubble, we can have this or this, and then this gives us our tuning parameter. And this works because we have few inputs and few outputs, okay? And in the middle, a very model which is quite rigid. And then at the end, this is the DNS in terms of mean flow field, in terms of the Fourier mode at the first harmonic. This is the forcing term, the Reynolds stresses, actually, with the divergence. And this is the reconstructed flow field. So you see, you have the mean, which is exactly the same. You have the first harmonic. This is the Fourier transform of the flow field, which is nearly the same. And also the Reynolds stresses, which are nicely recovered also. And just with nearly nothing, okay? We just had the length of the bubble. Just knowing the length of the bubble, we know all of this everywhere, okay? So this is a little, well, in this case, it works very well. Of course, I think in more difficult cases, it will work a little less good, but it is still something, an idea that works well, okay? So I just want to show you, this is just an experiment. It's just very, very frustrating of another, something which is an example. In this case, we had a jet. You see there is a round jet. There is air coming out here, okay, here. And we had laser measurements here, okay. And we had basically, we have these pictures where we have the jet coming here. You see we have high velocities here, low velocities here, and these are instabilities, Kelvin-Helmholtz instabilities that develop on this, okay? So my point here was to say, can we reconstruct these dynamics just from two things? First of all, if we know the mean, and just the dynamics at one point, with this resolvent stuff, we can reconstruct the full fluctuation, spatio-temporal fluctuation field everywhere. This, you see, we want to reconstruct this, knowing just the mean and this, okay? And for this is exactly the result of this. This is my PIV, okay? And this is the reconstruction of this, knowing just this and this. And how does it work? It works in a very simple way, is that as we know this, we can compute the resolvent modes H frequency, look at the dominant one, okay? And then these modes, we tune them at some point, their strength at some point with this, and then we can have the full flow field everywhere just by the knowledge of one point and the mean. And this comes from the fact that the fluctuations are spatio-temporally correlated, because these are coherent structures, turbulent coherent structures. And coherence means spatial and temporal. That means that at some point when it fluctuates, it means that at some other point it will also fluctuate, but in a slightly different way, but correlated. Okay? And the resolvent modes is just I would say a computation and evaluation of this correlation from point to point. And this is exactly what the resolvent mode manages to do, is to evaluate the correlation from point to point. And this is basically another example of the strength of the resolvent modes to try to represent the spatio-temporal correlation of complex flow fields, which can be turbulent, fully turbulent. Okay, and that's the slide of, that's the future of, but basically, well, I will not go into this. These are things where, well, of course, we'd like to go to complex geometries and things like this, but this is maybe not the point here. Okay. I just see that when I speak usually to fluids people. And I think it might be a little difficult for solid mechanics people, even very simple things like separation. Sorry for that.
Maybe we have time for a few questions.
Well, I do have a to just stop you, and it's beautiful talk. Thank you, Denis. I missed a little bit in the middle of it.
No problem.
So I have three questions. One is that you talked about variational methods.
Yeah.
And I was wondering, I mean, the case that you have with rants, it seems to be very easy to compute.
Yeah.
So what do you think would be the advantage of using derivative-free methods for the optimization? Would there be any advantage, or you think it's still in this case variational methods are good?
Well, I don't know, derivative free, but still in optimization.
But still in optimization.
I don't know if you speak more about genetic algorithms, things like this. Yeah, well, the problem is that here you have lots of degrees of freedom.
Yeah.
Usually when you make that kinds of stuff, it is several parameters. You can go up to, well, 100 is usually already a lot. But if you have 10 to the 6 or 10 to 7 numbers of degrees of freedom, it becomes very, very difficult. Okay? But then another way of making optimization is basically doing the ensemble methods, which is a way of optimizing, actually. And here you discretize your uncertainties by members, and it's even another way of optimizing. Okay, I think that all of this, it will work if the optimum is not that difficult to find. So that if you are uncertain parameters, you can still, well, it must be there. It should not be too difficult. Of course, optimization and adjoint-based methods are good when the space is extremely large and when you don't exactly know beforehand where the optimum is. Okay, so there is also the ensemble-based methods. You need to really discretize the uncertainties, while the adjoint methods is a little more blind. Okay, you give it and it will go down, and in the end he will find something. So it's usually a little more robust than the other methods, because in the other methods you have to think about the uncertain space and how you populate it. And in genetic algorithms, it's exactly this. You need algorithms to be clever, to go there, and once you have this, you go there. So there is also technology there. At some point, it becomes technological again in the other methods, but in a different way.
No, that answers my question. So then another thing is that when you were doing the modeling and you had the forcing on the right-hand side, FU and F nu T.
Yeah.
So FU is sort of a very general thing that you said.
Very general, yeah,
So
yeah.
I was wondering if you could use it and give it a little bit of a functionality to come up with better models. That,
Yeah. Well, actually, there is a whole thing at the moment which tries to couple what is there to make new turbulence models, actually. So basically, well, for example, if we have a new T, we have identified a new T there. As it stands at the moment, it's not a turbulence model because it's true just for this case. But then what people do, once they have a new T corrected part, they will put neural nets and make learning to link it, not just nu T of X to the point, but they will try to find a functional relation which links it to the state U bar and P bar, which is computed. So that at the end, if you have lots of different experiments, you make that data simulation which is there, which has nu T, and then you learn. You learn and learn and learn on lots of different configurations. You can pray and hope that you will have at the end a turbulence model which is good for at least all of them. And if you are really a good prayer, maybe it will even work for other configurations. And this is typically what people hope. You see, by learning on a backward-facing step, they learn on a recirculation bubble, they learn on a shock wave, and then at the end, maybe it will work for everybody, for everything. Yeah, exactly. But this is typically what people they are doing. Even at Onera, we do that. Yeah. We try to make a new turbulence model by learning with artificial intelligence and things like this. And there is a part which comes from data simulation.
Okay. So one last thing. Just one last
No problem.
So then for this last part, when you use the resolvent mode,
yeah.
Can you envision using some nodes that are coming from data decomposition rather than using the resultant nodes?
DMD
or POD, because POD is also some sort of correlation.
Yeah, well,
I was thinking here you have a RANS and you have a mean that is okay, but if you go, for example, for something that is like a Navier-Stokes equation that you're solving, or you're solving the full equation, then writing the resolvent wouldn't be as easy as if you were using the.
But I think that in some cases the Fourier modes are also the pod modes. Typically, if you have omega to omega 3 omega, usually you have 2 pod modes for the first mode, and in these cases it's easy. In this case where the spectrum is full, it's difficult. It's difficult, and so in the case when the spectrum is full, it's really in this case where the resolvent is interesting. Okay. And maybe in flow fields where the dynamics is peaked, oscillator flows. In this case, you could use pod, I think, but not in the general case jet flows where you have very broadband dynamics. In this case, I think you need a resolvent because pod, I don't know exactly how this will come. There is no, I think that in pod there is no reason that it reconstructs the Fourier mode, you see. While the resolvent mode, there are mathematical reasons for it, for it to do it, which are linked to shear-driven mean flows. They undergo Kelvin-Helmholtz instability, and this is the reason why the singular values pop up. So there are obvious reasons for it to work in lots of flows, actually.
Any other question? Okay.
Okay, so in your first approach, there was one free parameter. It was gamma in that regularizing term.
Yeah.
With we were penalizing the gradient of f.
Yeah.
So how do you choose that parameter?
This is, of course, a very empirical. The first thing we try to do is to normalize them so that they are order 1. But at the end, it's tuning. Obviously, tuning. There is no. You try from 0, then you increase, and then at some point. But the thing is that you can see it as something. Well, of course, I need to tune. But the problem of adding state covariance information is really a big problem, and it's not a problem that can be solved easily. It's about the uncertainty of the space of your model and the uncertainties that are inside, and evaluating this guy is not simple. In ensemble-based methods, it's a little simpler because you have members, and then you have an obvious evaluation of this. But you have an obvious evaluation of this, but you do the job at the beginning because you choose your members, so that you give a covariance to this term. So at some point you need to make this job of evaluating the state covariance of your model. So either you do it at the beginning when you choose your members, or at some points you need to do something like this. But I don't have a better answer to this question.
Okay. And may I have another one? So in your second approach, you are always using, for the verification, you are using direct numerical simulation, right?
Yeah.
So you are working with, let's say, exact measurements without experimental error.
Yeah.
So is it robust with
well,
experimental error?
I just show you things where we had exact measurements. But we also deal with corrupted measurements. Mm-hmm. And then we have lots of approaches. We Gaussian noise, outliers. You can treat in a theoretical way different kinds of noises. Okay, and it still works. But of course, you need to make it. You need to really come at the beginning that when you make the optimization, it's a compromise between the measurement and the state covariance. You always need to have this in mind somewhere. And of course, if you lose one term, it means something. So you have to be careful at what you do. But yeah, you can do that.
Okay, thank you.
Be the last one. I'm sorry.
No problem.
Well, the main hypothesis of the second part of your talk is related to the fact that it's rank 1.
Yeah.
Okay. So what do you think so you have to test it before in advance, in a way. So
yeah.
Why it's working so in so many cases, according to you?
Well, why it's working in so many cases? The reason is actually quite simple. Is that well, not that simple, but if you if you look at in that kind of flows, which are weakly non-parallel, okay, you can make a link between the optimal responses and spatial stability analysis, okay? And what you basically can show is that the singular value is something like the integral of the exponential alpha I. You see, if you make a spatial stability analysis, the alpha I, so that as soon as you have a convective, a spatial instability, okay, it will make pop up a singular value very high. And of course, you would not have it if you just had the resolvent at one point. You would have it a little, but the fact that you integrate, that it is the resolvent which is global here, okay, and that you integrate from here to here, it would make one singular value come out very, very strongly. And shear-dominated flows with inflection points always do that. Okay, so I think that as soon as you have shear flows with inflection points, you will have singular values that pop up in general.
And the following question, which is a usual one,
yeah,
has something to do with convective absolute?
No.
So if you have an absolute flow or global mode, for instance, it would work as well?
Yeah, well, as I already told, the resolvent is really interesting in the case of broadband flows. Okay, in the case when you have oscillator modes like the global mode, then you could replace the resolvent mode by a global mode which is usually marginal, but the resolvent mode at that frequency is the same as the global mode. So the resolvent approach encompasses the global mode, but the full thing is the same. It remains the same. But you can even be simpler in the case of oscillator flows because you don't need the resolvent. You can just look at the global mode, which is marginally stable, and it will be a little simpler. But it also works. But in this case, I agree that spatial stability analysis is maybe not good. I think the proof which is there works well here. Then afterwards, I don't exactly know when you have I don't know if you have a cylinder, you look at the mean. I don't even know if the mean is absolutely unstable. Maybe not. Usually the mean is marginally stable, as you know from Barclay and all that people. So it's not globally unstable, it's not stable, it's marginal. But maybe the argument which is there, which is alpha I, would still work. I don't know.
And the third question, very fast. You F nu and the first part, you have F nu and F, I don't remember, FU?
Yeah, FU and F nu T.
Do you, okay.
I can go.
I would say if you have FU,
yeah,
you need the second equation. Just put nu T to constant and play with FU.
Yeah, well, actually we've played a lot with this. Initially, when we started in 2014, we just did this. Just FU and no turbulence model. That works well when you have low Reynolds flow fields, Reynolds 100, 200, 1000 if you want. We did a profile with Beverly McKeown and Sean Simon, where we went up to, I think, Reynolds 10,000. But first it becomes numerically difficult, but this you could come over by taking some robust things. But at the end, if you go to very high Reynolds number flows, there is too much to be done with FU, and it doesn't work more from a fundamental point of view. And in this case, it's easier to have an order one thing which is approximately good, and then to correct it. At some point, if you have a very high Reynolds number flow, the space, the constraint which comes from the Navier-Stokes equation is not very big. You see, you have a freedom which is absolutely incredible by FU, and there is too much freedom. I would say. The equation doesn't constrain, and there is a whole valley of solutions, and then I think it's better if you do this. But you can play. There are lots of options. You can. I agree. You could froze Newt as it is, and then do FU. Here we did it coupled, but I think you have lots of choices. Okay.
C'est Resolvent Mode,
Ouais.
ça a à voir avec décomposer sur les premiers modes propres de l'opération ou pas?
Alors c'est pas des modes propres. Hein.
C'est plutôt
Non. En fait, généralement,